It turns out, if we fast forward to the present day, and a series of papers are still being written, so this is still research that's happening as we speak. But it turns out now that the general view, I would say the generally accepted view, is that black holes do not erase information from the universe. So in principle, if you could collect all that Hawking radiation emitted over eons, right, the lifetimes of some of these black holes, by the way, 10 to the power 120 years plus for some of the big ones. It's one with 120 noughts after it. And the universe is only one with 10 noughts after it years old at the moment, 10 billion years old or so. So we're talking about timescales vastly longer than the current age of the universe. But when they've gone, then in principle, we now think you could collect all that radiation, in principle, put it into some quantum computer, carry out some operations on all that radiation, and reconstruct the information about everything that fell in. But the implications of that, the mechanism by which that happens, I would say it's profoundly exciting, because it really does seem to be giving us a glimpse of a deeper theory of gravity. The simple way to say it, it seems that space and time are not fundamental. So one view, and I emphasize that there are other views, we're at the cutting edge of research now, but one view is a field which has become known as emergent space-time. So what does that mean? It means that space and time themselves are not fundamental. In Einstein's picture, we assume there is such a thing as space-time. This four-dimensional surface, manifold is the technical term, but you assume it's part of the model. There are such things as space and time woven together into the fabric of the universe. What they are, Einstein has nothing to say. It seems that there is a deeper theory underlying what we think of as space and time, which is a quantum theory. And so the idea is that space and time themselves emerge from what? From quantum entanglement, from some kind of smaller parts or pieces. We don't know what those things are. We don't know the nature of them. But it does seem that there's a deeper underlying theory from which space and time emerge. That is what we call the quantum theory of gravity. But the key thing to understand is we've been driven to that picture by asking very clearly defined, precise questions about how black holes behave, which goes all the way back to Einstein, and then to Stephen Hawking and many others' calculations through the 70s and 80s. But supermassive black holes are fascinating things. So these are the black holes that we have images of, radio telescope images. We have two images from a collaboration called the Event Horizon Collaboration. One of a black hole, it was the first one they acquired, of a black hole in a galaxy called M87, which is about 55 million light years away. This is a big galaxy, something like 1 trillion suns. And in the center of that, we've long suspected there was a black hole. Now we have an image of the black hole. It's a black hole that is so supermassive. It's over 6 billion times the mass of our sun. A big black hole by any measure. We also have an image, by the way, of the rather smaller supermassive black hole at the center of the Milky Way galaxy, which is only about just over 4 million times the mass of our sun. So it's a little one, but still big. We think that virtually every galaxy has a supermassive black hole at its heart. Caveat a little bit, because a couple of papers have been released recently suggesting that there may be galaxies observed where there are no supermassive black holes. There are lots of galaxies in the universe. Maybe there are exceptions, but it's fair to say that virtually every galaxy has a black hole at its center. That's an interesting observation because we don't know how those form. One of the reasons is we don't really fully understand how the first galaxies formed in the first place. It's current research, live research. One of the goals of the James Webb Space Telescope is to observe the formation of the first stars and galaxies. It can do that because it can detect very faint, very long wavelength light, which is what you need to detect if you want to look far out into the universe and therefore far back in time towards the origin of the first stars and galaxies. So the JWST, new instrument that's looking at that. There are also a series of new radio telescopes being built. The Square Kilometre Array, for example, in Australia and South Africa, which is a radio telescope array aimed at observing the formation of the first stars and galaxies. So this is live research. It's a fundamental question. How does structure form in the early universe? Not only are black holes interesting from a theoretical perspective, allowing us to peer or uncover deep questions or ask deep questions about the structure of space and time itself, but they're also key to understanding how galaxies form and how structures form in the early universe. How many black holes do we know of? So direct observation, in terms of radio telescopes, we have a direct observation of 2 of them from the Event Horizon Collaboration. The one in our galaxy, the Milky Way, and the one in the galaxy M87. We also have what I would call direct observation of black hole collisions. This is a completely different technology, a different approach. It's called gravitational wave astronomy. So gravitational waves are ripples in the fabric of the universe. Let's describe them like that. Although I once heard Kip Thorne call them a storm in time, which I think is also a very beautiful idea. And so the idea is that what is a ripple in space and time? They be passing through everywhere now, so through you and me, through the space in which we sit. And they're ripples in space and time, so time speeds up and slows down a bit as these things go through. Distances kind of shrink and expand a little bit as well. So they're real distortions in space and time. And they're caused by, well, actually, pretty much everything that happens in the universe at some level, but they're very, very faint and difficult to detect. The ripples we've been able to detect come from the collisions of black holes or the collisions of neutron stars. So these are highly energetic events in the universe. And the observatory is called LIGO and Virgo. These are essentially laser beams, so-called laser interferometers, about 2.5 miles actually long, 4 kilometers long, at right angles to each other. And they can detect little shifts in the distance between the mirrors between which the laser beams bounce, far, far smaller than the diameter of the nucleus of an atom. So tiny, tiny ripples in the fabric of the universe. By observing those ripples, we can see the collisions of black holes. We tend to see the collisions of big ones, and that's what's called a selection effect. The big ones are more energetic, and so the gravitational waves are easier to detect. But the collisions we're seeing are between black holes that are, for example, around 30 times the mass of our sun. And the number of those collisions is, I think it's fair to say, larger than anyone would have imagined before the observations were made. So it seems there are quite a lot of these black holes floating around that are very massive indeed, 30, 40 times the mass of our sun and upwards. And I think it's fair to say the formation of those things is a mystery as well. It's presumably that they're formed from the collapse of very massive stars, but the number of them, I think it's fair to say, took everybody by surprise. So we've detected, I don't know what the current number is actually, I'm speaking now in June 2023, there are collisions being detected reasonably often, but it's tens of collisions, maybe more actually. But it's we have multiple observations of collisions of black holes with black holes, and indeed black holes and neutron stars as well. So it's quite a few. So we're very certain now, as certain as we can be, that these things really exist. As I said, we have images and we have these wonderful observations of the collisions of them. Now, how many black holes might there be out there? There'll be billions of them, billions. So all massive stars that are, 3, 4, 5, 6, 7, 10 times the mass of the sun. There are lots of stars that are above the limit, beyond which we understand that at the end of their lives, when they run out of nuclear fuel, they will collapse without limit Nothing will stop the gravitational collapse, and they will inexorably form black holes. So black holes are the natural, we used to say, end point in the lives of stars above, 3-4 times the mass of our sun. We now know, of course, that ultimately those black holes will evaporate away again, but that really isn't in principle statement in the far future. So the way to think about black holes is that any star more than, let's say 3 or 4 times the mass of our sun and upwards, will form a black hole when it runs out of nuclear fuel at the end of its life. The numbers are kind of debated, but let's say something like 2 trillion galaxies, large galaxies and smaller galaxies in the observable universe. So 2,000 billion galaxies. Pretty much every one of those will have a supermassive black hole at its center as well. So we're talking about, not to steal Carl Sagan's phrase, but billions and billions of black holes. Carl Sagan said, "I never said that." So I'm not stealing Carl Sagan's phrase actually, because he says that he never said billions and billions. Let me give you some glimpses into why black holes are so fascinating and so perplexing and wonderful. So if we go back right to the beginning of the work on black holes in the 1970s, Jacob Bekenstein, a colleague of Stephen Hawking's, actually, one of the first researchers to really begin working on black holes alongside greats like John Wheeler, for example. Bekenstein noticed in a simple calculation, which was initially pretty much a back-of-the-envelope calculation, actually, noticed that you can answer the question, how much information can a black hole store? That's a strange thing to say, because the model of a black hole is pure geometry, pure space-time. So you might think, well, it's not capable of storing any information. Now, how does something store information? You need some structure, you need atoms, or something that can store bits of information. Well, it turns out that you can calculate that a black hole stores information, and how much. This is the fascinating thing. So it stores in bits. The information content is equal to the surface area of the event horizon in square Planck units. What's a Planck unit? It's a fundamental distance in the universe that you can calculate by putting together things like the strength of gravity, Planck's constant, speed of light. It's the smallest distance, often described as the smallest distance that we can talk about sensibly in physics as we understand it, the Planck length. This is a bizarre result. There's so many things that are bizarre about that. The questions it raises: what's storing the information? How is the information stored? Why is the information content of a region of space equal to, or why does it have anything at all to do with the surface area surrounding that region rather than the volume? If I asked you how much information can you store in your room, the room that you're sitting in now, let's say it's a library, then you would say, well, it's to do with how many books I can fit in the room, or hard drives, or whatever it is, right? It's to do with the volume of the room, the space. But black holes seem to be telling us that there's something about the surface surrounding a region which is fundamental. This is the first glimpse, I think, of an idea called holography, which now seems to be correct in a sense. So holography, what is that? It's the idea that there are different descriptions of our reality. There's one description which is the description that we're all comfortable with and familiar with, I would say, which is that we live in this space, the 3 dimensions of space, and time is a thing that ticks. And Einstein told us that they're kind of mixed up, but still you have this picture of space being this, right, the thing in which we exist. There's an equivalent description, it seems, and it's been proved, by the way, for a very specific model called ADS-CFT by a physicist called Maldacena. There's an equivalent description which is of a theory that lives purely on the boundary of the space. And it's absolutely equivalent. It's an absolute perfect description, a dual theory of the description of the space itself in the interior of this region. That's called holography because if you think about what a hologram is, then at the very simplest level, it's a piece of film. But that piece of film contains all the information to make a three-dimensional image. So all the information about a three-dimensional image is contained on a two-dimensional piece of film. It's basically a hologram. And it seems from our study of black holes, and the hints go all the way back to the 1970s to Jacob Bekenstein's work, that our universe is like that in a way that's not fully understood yet. The picture is that, and physicists, I always like to joke, when they don't really know or the language isn't present, then physicists often say in some sense, and wave their hands. So in some sense, there's an equivalent description of our reality, which lives on a boundary surrounding it. It's perfectly equivalent. And you might ask the question, well, what's the real description of reality? And the answer is we don't know, but they're equivalent. So it's strongly suggestive that there's let me say a deeper theory, but at least a difference theory of our experience of the world, of space and time, that does not have space and time in it. And that's one of the wonderful surprises that's really emerged from, at least in part, from the study of black holes and the attempt to answer the very well-posed questions that black holes pose. I should say that the work done by Maldacena, the ADS-CFT correspondence, was purely mathematical. So it wasn't framed in the study of black holes, although the questions ultimately seem to be intimately related. So that's number one. So the study of black holes seems to be strongly suggesting that these ideas of holography, holographic universe, which came from a different region of physics, actually, from trying to understand other things, those descriptions may be valid, may be useful, may be in some sense true. The other remarkable thing for me, I think, in the study of black holes, is an intimate relationship between black hole physics and quantum computing. This was wholly unexpected, I think it's fair to say. The relationship comes by saying, okay, so there's a theory on a boundary, a quantum theory, which is a perfect description, a dual description of the physics of the interior of a region of space. You might say then, well, how is information encoded on this boundary? How does that relate to the physics of the interior, space and time? And it seems that we're beginning to glimpse an answer, at least in very simplified models. And it seems that the information is stored on the boundary redundantly, which means that you can lose a bit of it and still fully specify the physics of the interior. Redundant storage of information. Now, if we go to quantum computers, there's an engineering challenge in building quantum computers. And just to emphasize, we have these things. They're not theoretical, they exist in labs across the world. There's a challenge, which is how to store information in the memory of the quantum computer safely, robustly, because quantum computer memory is notoriously susceptible to any interference from the outside environment. If any of the environment in which the memory sits interacts with the memory in any way, then the information is destroyed. So it's a tremendous challenge. And there are deep problems associated with the fact that you can't copy information in quantum mechanics, which is basically the way that your iPhone or whatever it is stores information and prevents errors entering into the memory of the computers that we're all familiar with. It's basically copying information. You can't do that in quantum mechanics. Fundamental. It's called the no cloning theorem. Engineers have had to develop very clever algorithms and ways of trying to store information in quantum computer memory and build the memory such that it's resilient to errors. And it turns out that the solutions that are being proposed and explored look like the solutions that nature itself uses in building space and time from the theory, the quantum theory that lives on the boundary. It's really strange. And I just emphasize, you're not meant to understand what I've just said, because I don't understand what I've just said, because nobody understands what I've just said, right? We're catching glimpses of this theory. And that's where the research is at the moment. It's right, it's tremendously exciting. There's papers being published all the time that are digging more deeply. They're suggesting pictures of reality, physical pictures of what's happening. But there's no sense, and I emphasize it, in which everybody agrees on these pictures. So I'm giving you an interpretation, and there will be other people who have different interpretations. But it does seem that whatever this quantum theory is that underlies our reality, then there's some redundancy in the way the information is stored in that quantum theory. And it does seem that that's akin to or similar to the way that we will in the future encode information in the memory of quantum computers to protect them from errors, called a quantum error correction code in the jargon. I find that fascinating. It's tantalizing. It's a glimpse of something Einstein said. There's a beautiful phrase, which actually the physicist Sean Carroll used as a title of one of his books on this. Einstein said that if you look at nature really carefully and keep pulling at the intellectual threads and keep going and just keep delving down into what nature seems to be trying to tell us, then if you're lucky and persistent, you can catch a glimpse of something deeply hidden. It's beautiful, that, isn't it? A glimpse of something deeply hidden, which is the deep underlying structure of nature. And it does seem that we're beginning to glimpse something deeply hidden. From the study of black holes, the related, surprisingly, field of quantum computing and quantum information, we're glimpsing something deeply hidden, the deep underlying structure of reality itself. And I think it's very beautiful. No one really knows, I think it's fair to say, where this is going, but they're hints of something deeply hidden. Black holes may well help us understand a different but related question, which is what happened at the beginning of the universe. So I think black holes are, at the moment, the most interesting naturally occurring objects, in the sense that they're helping us understand, or forcing us into a deeper understanding of what space and time are. And my view is that if we're going to talk about the origin of the universe, even ask questions such as, did the universe have a beginning in time, which we don't know the answer to, then it surely seems to me that we have to understand what space and time are before we can ask and have any chance of answering such questions. And black holes, it turns out, are the objects that we can see, that we can observe, that actually exist in nature, that force us down that route to ask questions, sharp, well-defined questions actually, about the nature of space and time themselves. It surely must be the case that as we get a deeper understanding of what let's call it the fabric of the universe is, then we can begin to get a rather deeper understanding or more insight into questions about the origin of the universe itself, should it have one. I mean, why do I keep saying should it have one, by the way? Because you might be watching this saying, well, it's a Big Bang. We know there's a Big Bang, and that's true, we do know there was a thing called the Big Bang. What do we mean by that, though? We mean that 13.8 billion years ago, the universe was very hot and very dense everywhere. The region of space that now forms the room in which you sit was very hot and very dense 13.8 billion years ago. We know that all the galaxies are receding from each other at the moment, and just put very simply, if we make the measurements of how they're receding and run time backwards, then you find that they're all on top of each other 13.8 billion years ago. So we know something interesting happened back then. We have a measurement to it. It's not up for debate. Often when people say, well, how do you know about this Big Bang thing? The vast amount of evidence that such a thing happened, the best evidence probably is you can see it. So we see something called the cosmic microwave background radiation, which is the universe as it was about 380,000 years after the Big Bang. What we see there, we have a photograph of it, is a universe that was very different from the one we see today. There were no stars, no planets, no galaxies. It's just a hot, glowing mass of gas, primarily hydrogen and helium, and we have a photograph of that. So we know something interesting happened. But do we know that that was the origin of the universe? No, we don't. We have theories, strong physical pictures of the universe before the Big Bang, in a very precise sense, before the universe was hot and dense. Theories called inflation, which say that space was still there and it was expanding very fast. And then that fast expansion drew to a close, and all the energy driving that expansion got dumped into space, made particles, and that's what we call the Big Bang, the so-called hot Big Bang, as we term it today. What happened to start inflation off? The answer is we don't know. When did inflation start? We don't know. We have a minimum time that it needed to go on for, but we don't know what or even if that phase of the universe constitutes a beginning. There are so many reasons to study black holes. There's fascinating, beautiful things that we know to exist in the universe, pose fundamental questions. But one of the reasons that we're really interested in them is that, put it this way, there's singularities at the end of time. Right? The Einstein description says that inside a black hole there's a singularity, and locally, at least in that region of the universe, that constitutes the end of time. There's a singularity, maybe, at the beginning of time, the other end of time, if you like, that we're also interested in. Might be you might call it the Big Bang singularity, the origin of the universe. And it seems to me to understand that singularity at the beginning of time, the Big Bang singularity, then we need to understand the singularities at the end of time. And the great benefit is we can see those. So we can watch them bump into each other. We can see them at the centers of galaxies. We can make observations of them, and we can do calculations. Understanding black holes, I think, will be the key to a deeper theory of our universe. So in that sense, I think it is fair to say that black holes are the keys to understanding the universe.